So the integral we've got here is between 0 and infinity. We've got two polynomials, p and q, but they're now of alpha, x to the alpha, where alpha can be any number greater than 1, so it doesn't have to be an integer. The condition we have is that the degree of q must be larger than the degree of p, so it must be at least 1 larger than the degree of p. And also the polynomial q is not allowed to have any zeros along the real positive axis. Okay, so the trick for doing this integral is to use a somewhat unusually shaped contour. We'll see why this is fairly soon. We're going to have a sector-shaped contour where the angle is 2 pi over alpha. Again, this is a sector of radius r, which will go to infinity. This is our contour. And we're going to consider the limit as r goes to infinity of the contour integral of pz to the alpha dz over qz to the alpha. So, looking at it piece by piece, the first bit from here to here, as r goes to infinity, is the integral we want. So just along here, dz is equal to dx. So we just get I. The next bit is along here. So it's the limit as r goes to infinity of the integral. Now it's a d theta integral. We're changing the angle theta, so it's from theta equals 0 to 2 pi over alpha. And it's the integral of p. Now we're changing variables. Here we've got z equals r e to the I theta around here. So we've got z now is r to the alpha e to the I alpha theta, and dz is dr is r times I times e to the I theta d theta. And we've got q, the same thing on the bottom. Okay, so what we're interested in is this, we need to show this is going to go to 0. So it's going to be of order r plus 1, and then we're going to have, well, it's going to be the degree of p, but it's also raised to the power alpha, so it would be plus alpha times the degree of p, and we've got degree of q on the bottom, so it would be minus degree of q on the bottom. So overall, even if the degree of p minus the degree of q is just minus 1, because alpha is greater than 1, this is going to be negative overall, as long as this is satisfied. So therefore, this is going to be r to some negative power, which will go to 0 as r goes to infinity. So this will tend to 0, and we're fine. But we've got one bit left we didn't have before, which is from here to here. So what's happening along here is that z is now little r, which is varying, and theta is constant. So theta is e to the I 2 pi over alpha. So now if we substitute that into this expression here, what do we get? Well, now the integration variable is r, and r is varying from infinity to 0. So we have plus infinity to 0. And this is the clever bit. So you see p, when we substitute z to the alpha, what do we get? So we get r to the alpha. But you see e to the I 2 pi over alpha raised to the power alpha. That just cancels that alpha, and we get e to the I 2 pi, which is 1. So we just get p of r to the alpha. And dz turns into dr times e to the I 2 pi over alpha. So we can take the 2 pi e to the I 2 pi over alpha out the front. And on the bottom, the same thing happens. So we just got Q. Okay. Now this expression here, if we change the r to the x, it doesn't matter whether we have r or x, is the same as this, but with the limits swapped. So all we have to do is swap the limits and get a minus sign, and then we have basically this thing times I with a minus sign. So that means that we have the result 1 minus e to the I 2 pi over alpha times I is, by the residue theorem, 2 pi I times the sum of the residues of P over Q at Zj, where this time we need all of the poles inside the sector. So a neat way of saying that is that the argument of Zj, the poles at Zj, needs to be between 0 and 2 pi over alpha. So we can say that argument of Zj needs to be between 0 and 2 pi over alpha. Okay, do principal value.